Hello and welcome to a three-part or three-module unit on mechanical waves. In this unit, we're going to try to accomplish the following objectives. Number one, we're first going to begin by defining what is meant by a mechanical wave. We'll also take a look at the connections between simple harmonic motion, which we've just recently studied, and periodic mechanical waves. We'll also take a look at something called the wave equation and be able to not only state it, but also to apply it to a given situation involving waves. We're going to be able to compare and contrast longitudinal transverse waves and give examples of each one. And then we'll move on to look at how we can predict the result of interference of two waves, and also to predict the result of a wave interacting with a boundary. So let's start by taking a look at what mechanical waves actually are. A mechanical wave is the motion of a disturbance through an elastic medium by which energy is transmitted. So a mechanical wave must have all three of those features to be considered a wave. What you're looking at, what's very different, and we're going to see in a few of the slides coming up down the line a piece here, is that for the first time in the course, we're not necessarily looking at a specific particle or a specific object and its motion and forces and energy involved in that, but we're actually looking at the disturbance of particles within an object. And so that's a little bit different. It'll take a little bit of variation on the way we've approached things previously. When we talk about an elastic medium, we're talking about deformable matter, and even that term may seem a little bit new to you, and all it is just matter in general, because all matter is deformable. All matter is elastic in some form or fashion. We think about things like rubber as being an elastic medium, and it is, and it's highly elastic, and that's why it's easy to imagine it, and we've had that experience of stretching it. But believe it or not, something like steel is also deformable and elastic, and it can support mechanical waves traveling through it just a lot differently than a material that we would normally consider to be elastic in terms of being very stretchy, for lack of a better term. And then finally, the most important element of this, because if all we were looking at was a disturbance through an elastic medium, through matter, that might be a curiosity at best, but what is really important is the fact that energy can be transmitted from one place to another through this disturbance that's traveling through an elastic medium. For example, the medium through which you're hearing me right now is air, and that disturbance, that mechanical wave that's responsible for that ability for you to hear, is sound, and there's energy involved. I produce energy. It's captured by the computer. It's then transmitted from your speakers on your side out, and you're able to hear it. And that's a perfect example of a mechanical wave, and a very important one for that matter. So whenever we start a new concept, and there's a whole broad array of phenomena that are associated with it, you know that we typically try and get things organized in the beginning, so that it's not just a mixture of seemingly unrelated content. So we're going to do the same with waves. So with waves, there's two ways that you can, there's several ways you can actually organize the waves. One way is to look at types of waves by their source. And basically what we're looking at is essentially two things: a pulse wave and a periodic wave. And you're going to see examples of this. This unit is one that really is going to rely a lot on graphical representations. It's just the nature of, because you're not looking at a particle, you're looking at a disturbance within a material. It really helps to be able to visualize it. So a pulse wave, we're going to see, is just simply a wave that just looks like it has a single pulse, a single arch, not that ongoing familiar up and down undulating shape that you associate with waves. That particular type of wave is called a periodic wave, and it's the one, if we trace back to our study of simple harmonic motion, a simple harmonic oscillator that is attached to an elastic medium will cause a continual series of pulses that is what we consider a periodic wave that continues to repeat itself on a regular basis. So graphically, here's what you're looking at. A pulse wave, in my mind, is just a single disturbance, a one-time thing. One example of this that you might think of is a snap on a whip kind of a thing, or anything that's similar to that, where you just get that one disturbance and it travels through. In this case, you see in this diagram the whip. That's a pulse wave. A periodic wave has that more familiar shape that you're used to, that wave shape. It's actually something that we call sinusoidal mathematically, but that level of mathematics we're not going to introduce here, at least not at this point. So those are one way that you can represent waves, is the nature of the source. Was it a single pulse or an occasional pulse, or is it something that's an ongoing, regular, periodic disturbance? Another very important point, I've alluded to it earlier, and I'll probably allude to it several times throughout, is the fact that what we're looking at here is not single particles, but the disturbance of particles in an elastic medium. In this case, the elastic medium is this piece of rope, or whatever is represented here. And the point is this, and it's extremely important, and that is that the wave is traveling this way, but yet the little individual pieces of the rope, these little rectangular pieces that represent sort of small, particles, for lack of a better term, only go up and down. The rope that's here by this person's hand who's making the wave move, this piece of rope here isn't traveling all the way down here and coming back. All it's doing is going up and down in place. And so is this piece of rope right here, just going up and down in place, and this one, and so forth. And so what's moving is the disturbance, even though the particles are more or less staying in the same neighborhood that they're in. The particles are moving up and down in this case, but they're not moving along the path of the wave.